Ladies and gentlemen, welcome back to Lesson 10 in Group Theory. Here we will cover what is called a cyclic group, a very interesting type of group with a lot of results that arise from it. So, to hint at the word cyclic, we need to look at this example that I put on the right here. So consider this cycle of integers starting from 0 and increasing as we go out of the spiral. So here we have that, notice, we have that 0, 4, and 8. They all lie on the same line, and they are all multiples of 4. And over here we have the multiples of 4 plus 1. Here we have the multiples of 4 plus 2. Here we have the multiples of 4 plus 3. And we see that these classes all form these classes make up the entirety of the integers starting from 0. And if we come up with z for z, the collapsing of the integers modulo 4, we will see that all of these numbers on the first line, they get collapsed into a single element, which is the class of 0. So of course we can write down the class of 4, which is the same as saying the class of 0 or the class of 8. But the idea here is that all of these elements are represented by a single element here. And on the right, all of these elements are represented by a single residue class, which is 1 or 5 or whatever, but 1 is what we choose here. And here, all of them will be represented in a single residue class, which is 2. Same goes for here, 3 bar. So in the end, we have that z for z has only 4 classes, 0, 1, 2, and 3. And we've successfully took all of the integers and reduced them modulo 4. And z for z is an example of a cyclic group because it's going to be repeating over itself over and over again. So that was a very rough definition. The actual definition of a cyclic group comes from the fact that we've took in lesson 4 that groups can be presented in a presentation using generators and relations. Remember, generators are elements that can generate the entire group. In other words, any element in the group can be written as a product of these generators or the inverse of these generators. So, for example, if we had A and B generating the whole group G, then A and B would be called the generators. Now, cyclic groups are groups which are generated by a single element. In other words, if G is equal to just the group generated by A, in that case, we would call G a cyclic group. And A, in this case, would be the generating element of G. So we will look into that, and afterwards we are going to see a very set of interesting results. It's going to be, first of all, some theorems that we'll see, some propositions, and I'm going to tell you here that the propositions will be proved in this lesson, but the theorems will be proved in the next lesson so that the video won't be too long. So the results that we're going to be see include the uniqueness of cyclic groups up to isomorphism, enabling us to easily classify all of the cyclic groups that there are. And we're going to be talking about the powers of the generating element. And lastly, we're going to be talking about the subgroups of these cyclic groups and what do they look like, and some examples on that. So let's get started. Let us start with a formal definition of a cyclic group. A group G is said to be cyclic if G is generated by a single element. In other words, G is composed of all the powers of G where R is an integer. So R could be a negative number, a positive number, or 0. And in the case that R is 0, we would have G to the power 0 is the identity in G. G is a group, and you can prove that yourself using the group properties, associativity, identity, closed under the operation, and inverses. Examples of cyclic groups, the first one being just the set of all the integers z under the operation addition. So z would be generated by a single element, which is 1 in this case. So it would be all the powers of 1. Well, when I say powers here, I do not mean multiplicative powers. Remember, the operation of the group is plus. So actually, I'm saying the additive powers of 1. So the additive power of 1 is done by adding 1 to itself multiple times. So it is done by n times 1, not 1 to the power of n. So n times 1, where n is a integer. And this equals all the integers. -3, -2, -1, 0, 1, 2, 3, and so on. So the whole group Z can be generated by a single element, which is 1. Notice that the whole group can also be generated by -1, where we take -1, and instead of n, it would be just the negative of n. So if you want to generate 5 from -1, you just multiply -1 by -5, and you're good to go. So the generator is not necessarily unique. We could have multiple generators of the same group. However, all of this to say is that the entire group can be generated by a single element, and that's what makes it a cyclic group. The next example shows us the example I've showed you earlier, which is z/mz. So the integers collapsed modulo m with the operation of addition. So this means that this would be the set generated by the residue class of 1 times n. So the additive powers of the residue class of 1, where n again is an integer. And this gives us, at the end of the day, 0 bar, 1 bar, 2 bar, all the way to m minus 1 bar. So all the residue classes from 0 to m minus 1 bar, and any other residue class, any other representative such as m, would be just equal back to 0. So in fact, we will just be repeating the elements, and we do not need to include m in the set because it's already represented by 0. So the entire group is represented by only these elements, and it's all generated by a single element, which is 1 bar. The next example shows us one of the subgroups that we've seen of D2N, the dihedral group, which is the group generated by the rotations. So this is the identity r, r squared, r cubed, r to the 3, r to the 4, all the way to r to the n minus 1. And this is equal to r to the k, for k being any integer. By definition, this is a cyclic group because it is generated by r. So any element in the group is a power of r. And this we've seen, it is a subgroup of the dihedral group D2N. Before we get into the last example, I'd like to bring to your attention or to remind you of Euler's beautiful formula. So for Euler's beautiful formula, we have that e to the pi I is equal to cosine. So for Euler's beautiful formula, we have that e to the ai is equal to cosine of a plus I sine of a. So let's use that identity here. So what if a is equal to 2 pi? So e to the 2 pi I is equal to cosine of 2 pi plus I sine of 2 pi. That is equal to, well, cosine of 2 pi is equal to 1, and sine of 2 pi is equal to 0, giving us 1. So e to the 2 times pi times I is equal to 1. How nice is that? So we're going to be using this construction to get the nth root of 1. So let us take the nth root of these two elements. So if you take the nth root, this is just equal to the nth root of 1. And let's say what happens when we use exponent laws here. We get e to the 2 pi I divided by n. In other words, what is the element that if you take the nth power of the element, you get back 1? And that is exactly this element, because e to the 2 pi I divided by n taken to the nth power gives e to the 2 pi I, which is equal to 1, which means this is called the nth root of unity. And it turns out that we only need this element here to generate a group of all the nth roots of unity. And this is a cyclic group because it's all generated by a single element, which is the nth root of unity here. Let us take an example. So for an example, let's take n is equal to 4. So if n is equal to 4, we would have e to the 2 pi I divided by 4. This would be e to the pi over 2i. Using Euler's formula, this is equal to cosine of pi over 2 plus I sine of pi over 2. Cosine pi over 2 is equal to 0, and sine of pi over 2 is equal to 1, which equals to I. So I is the generating element when n is equal to 4. So we would have I to the k for k being an integer. And this equals the set containing I, minus 1, minus I, and 1. Just the first, second, and third, and fourth powers of I. And fifth power, sixth power, seventh power, minus second, minus third, minus fourth, they all give the same elements that are in this group. So in fact, I is the generating element, and this is a cyclic group, a cyclic multiplicative group. And this can be done for n is equal to 5, n is equal to 6, n is equal to 7. And if you look at it on the Cartesian plane, where the real part is the x-axis, the imaginary part is the y-axis, and you draw the unit circle, you would find that for n is equal to 4, we would have the 4 points 1, I, minus 1, and minus I. So it not only gives a very nice algebraic description of the group, it gives a very nice geometric interpretation of the group as well. Let us now move into the discussion of the generating element. The main idea here is that we're going to be discussing what the order of the generating element of the cyclic group is. In proposition 1, we say that if G is the cyclic group that is G to the k, where k is an integer, in other words, it is generated by the element G, then the order of G is equal to the order of small g. Before we get into the proof, note that the order of big G as a set of elements is just the number of elements in big G. But the order of small g as an element is the smallest integer, such that if you take the element to the integer power, then we get back the identity element. So just keep that distinction in mind as we go through the proof. For the proof, we have two cases. One is where G is finite, the other where G is infinite. If G is a finite group, in other words, if the order of big G is equal to R for some finite R, then we can list all of the elements in G using the description that is given here. So if k is equal to 0, then it's g to the 0, but that's equal to the identity. If k is equal to 1, that's g, and then followed by g squared, g cubed, all the way to g to the r minus 1. What happens at r? So if we write down g to the r, we would have counted r plus 1 elements. But this is not true because the order of g is only r. We cannot have r plus 1 elements. That's too many elements. So we need to say that g to the r is going to go back to the identity. So g to the r is equal to 1. And we clearly see that g to the I is not equal to 1 for all I that is between 0 and r. Because for all these i's, we have that g to the I gives one of the elements that is here, and they're all not equal to 1 clearly because we just listed them. So this gives that, by definition, the order of g must be equal to r. So this element is just the identity, and we have only these elements here, thus completing the first case where g is finite. Now, if g is infinite, then because we have an infinite number of elements, we would have 1, g squared, infinite. So we would have that g to the a is not equal to g to the b if a is not equal to b. We would have that g to the a is not equal to g to the b if a is not equal to b, because any element that if you multiply g by it, that means that any power of g with any different power of g will never give the same element, because remember, we have an infinite number of elements. So we keep multiplying g by itself, we have different elements. So this means that there does not exist a positive r such that g to the r is equal to g to the 0, because r is not equal to 0. So g to the r is not equal to g to the 0. So because there does not exist any r such that g to the r is equal to the identity element, by definition of the order of g, this means that the order of g is equal to infinity. If you've forgotten what the definition of the order of g is, I recommend you go back to lesson 3 and check it out. Now, proposition 1 is very important, and we're going to be using it a lot to know the order of an element of a cyclic group. But proposition 2, I'd say, is equally as important. And let's see why. So proposition 2 says that if G is a group and G is an element in G, and we have some integers m and n such that G to the n is equal to the identity and G to the m is equal to the identity, then G to the GCD of nm is also equal to the identity. In particular, if G to the m is equal to the identity, then the order of G divides m. To prove this result, we will use Bezout's identity. Bezout's identity says what? It says that, so by Bezout's identity, a very useful identity concerning the GCD of two numbers, we have that the GCD of n and m is equal to Rm plus Sn for some integers r and s. After that, we will take g to the power of the GCD to see what that gives us. So g to the GCD of nm, we'd like it to give us the identity, so that's what we expect using Bezout's identity. So we will get g to the power Rm plus Sn, and this equals, by exponent laws, g to the Rm, g to the Sn, and now we're going to use the fact that g to the n and g to the m are the identity, so we're going to isolate these a bit. G to the m to the r times g to the n to the s, this is equal to identity to the r times identity to the s, which is equal to the identity, thus proving the first part of the proposition. So now that we have proved the first part of the proposition, let us prove the second part, where it says if g to the m is equal to 1, then the order of g divides m. So if g to the m is equal to 1, we have two cases to study. The first case is when m is equal to 0. Well, if m is equal to 0, and we want to prove that the order of g divides m, so we want to say that the order of g divides 0. Is that true? Yes, it's always true, because for any integer, not only the order, any integer, k divides 0 for all integers k, since 0 divided by k is equal to, you guessed it, 0, which is an integer. So this is automatically true. Now, for the second part, it's a bit longer than the first part, admittedly, but we can easily reach there. So the second part, we have that m is non-zero. So if m is non-zero, we know by definition of the order of g, we know that if we take g to the power of the order of g, we would get back the identity element, right? Because it's the smallest power of g that gives the identity. So if we have this and we have that, we have two different integers, maybe the same, but two integers such that g to the m and g to the order of g gives back the identity. Therefore, we can use this result here by replacing n by the order of g. So g to the GCD of the order of g and m is equal to 1. Okay? Now, since the order of g is the smallest power of g giving the identity, we have necessarily that g is at most GCD of g and m, because we've just seen that this number here, if we take g to the power of that number, we get the identity, and so therefore this number has to be bigger than or equal to the order of g. On the other hand, we have that the GCD of g and m, because it's a GCD, greatest common factor, it has to divide both the order of g and m. So it divides the order of g, but if it divides the order of g, it cannot be greater than the order of g. It has to be less than or equal to the order of g. So we've just proved the inequality in both directions. So necessarily they have to be equal to each other, because if 3 is less than or equal to 3 and 3 is greater than or equal to 3, then of course 3 is equal to 3. So we have that the GCD of the order of g and m is equal to the order of g. But this just means that the order of g divides m. And a clear example would be, for example, GCD of 2 and 6. that is equal to 2, implying that 2 divides 6. Okay, so this proves the second and final part of the proposition where the order of G divides M. So for example, if we know for a fact that G to the 10 is equal to the identity, then we can guess that the order of G is equal to either 1, 2, 5, or 10. In other words, all the possible divisors of 10. And now we have completed the proposition. Let us now talk about a powerful result about the classification of cyclic groups. Because group theory is all about trying to classify and trying to identify all of the groups that are possible. Literally speaking, it is impossible to classify all of the groups, but it is easier and more practical to classify them up to isomorphisms. What does that mean? It means that for all our intents and purposes, two groups which are isomorphic are essentially the same. So they're all classified under the same representation. If we had group A and group B, which are isomorphic to each other, we will not treat them as distinct groups. We will treat them as the same group. So this is the idea we're going to be employing in Theorem 1 here. Two cyclic groups of equal order are isomorphic. So two cyclic groups that have the same number of elements are considered to be the same group. And so we classify all of the groups that have the same order, all of the cyclic groups that have the same order, into a notation that we call Cn or Zn. So even if we had an infinite number of groups, but they all had the order 5, then we would have C5 representing all of these cyclic groups, and we wouldn't care that these cyclic groups are different. We would just care about the number of elements in them. So they're all classified as Cn or Zn, or even Z and Z. And the proof of the theorem, like I said before, will be done in the next video, so stay tuned for that. Let us now discuss the order of the power of an element in a group. Before we get into the proposition, I'd like to emphasize that G is any group, not necessarily a cyclic group. So in proposition 3, we have that if G is a group and G is an element in G and A is a non-zero integer, the first thing is that if the order of G is infinite, then the order of the 8th power of G is also infinite. The second result says that if the order of G is finite and equals n, then the order of the 8th power of G is equal to n over the GCD of an. Thirdly, we have that if the order of G is equal to n and a is a positive integer that divides n, then we have that the order of the 8th power of G is n divided by a. Let's get started with the proof. The proof of this proposition will be done by contradiction. We will suppose that it is not the case that we have this, and then we will reach a contradiction which will force us to conclude that it must be this case. So suppose not that the order of G is in fact infinite, but the order of G to the A is not infinite. It's equal to L, which is finite. So looking at the order of G to the A being L, we can use the definition of that to say that G to the A to the L equals 1. But we know that G to the A to the L is equal to G to the AL. So we see that G to the power AL gives us the identity. So if we look at the order of G, by the proposition seen earlier, we know that it must divide AL, because AL is a power such that g to that power gives the identity. So the order must divide AL. If it divides AL, that means it is less than or equal to AL. And AL, of course, is just a number, a finite number. And since it's finite and infinite at the same time, we arrive at a contradiction. Therefore, the order of g to the a must be equal to infinity, since that is the opposite of what we supposed. Completing the first part of the proof. The proof of the first part is going to be done by contradiction. So we suppose something that will lead us to a contradiction, and then we reach the conclusion that it must be the opposite of what we supposed. Suppose not that the order of g is infinite, but the order of g to the power a is not infinite. It is equal to L. So L is finite. So this means, by definition of the order of g to the a, that g to the a to the L is equal to the identity. But g to the a to the L is equal to g to the a L. And this means that by the proposition that we've seen earlier, AL has to be divisible by the order of g to the a. This means that g to the a divides AL. If it divides AL, this means that g to the a The proof of the first part will be done by supposing something and then reaching a conclusion where we're forced to suppose the other thing because there is a contradiction. So, the proof of this proposition will be done by contradiction. We will suppose that it is not the case that we have this, and then we will reach a contradiction which will force us to conclude that it must be this case. So suppose not that the order of g is in fact infinite, but the order of g to the a is not infinite. It's equal to L, which is finite. So looking at the order of g to the a being L, we can use the definition of that to say that g to the a to the L equals 1. But we know that g to the a to the L is equal to g to the a L. So we see that g to the power AL gives us the identity. So if we look at the order of g, by the proposition seen earlier, we know that it must divide AL because AL is a power such that g to that power gives the identity. So the order must divide AL. If it divides AL, that means it is less than or equal to AL. And AL, of course, is just a number, a finite number. And since it's finite and infinite at the same time, we arrive at a contradiction. Therefore, the order of g to the a must be equal to infinity, since that is the opposite of what we supposed. Completing the first part of the proof. The second part of the proof we will prove it directly. No contradiction needed. So we want to prove first that g to the a to the this power gives us the identity, because that is one of the parts of the definition of the order. So if we take g to the a and we take it to the power of n over the GCD of an, we should get back the identity. Okay, so here we have this is equal to g to the an over GCD of an by an exponent law, and this equals to g to the n, so I isolate g to the n, to the power a over the GCD of an. But we've supposed here that the order of g is equal to n, so g to the n is equal to the identity. So it's identity to the power a GCD an, and the GCD of an divides a. So there is no problem dividing a by the GCD. We get an integer, and 1 to the power of an integer gives back 1. So this is well and good. So now we know that the order must divide n over the GCD of an. So let L be equal to the order of g to the 8th power. We just saw, as I've mentioned, that L, the order of g to the a, divides n over the GCD of an, because we've just saw that ga to that power gives the identity. So I will put a star here to indicate this relation, which we will use later. So we have this relation, and we want to show that n over the GCD of an divides L, and we will call that a double star. And if A divides B and B divides A, then that means that A equals B if A and B are both positive. And that is the case here, that L is positive, N is positive, the GCD is positive. So this is the idea of what we're trying to prove here. So we want to reach this result, and how we're going to do that? We're going to say that 1, the identity, is equal to g to the a to the L, because L is the order of g to the a. And that makes sense. And that is equal to g to the AL. So g to the AL, this power gives the identity, meaning that the order of g must divide AL by the definition of the order of g and the proposition we've seen earlier. And we have that the order of g is equal to n, because we've just called it n here. So it's just going to be n dividing a times L. We will now divide both sides of this relation by the GCD of a and n. So this means that n divided by the GCD of an divides AL over the GCD of an. So I'm going to put the L here to make it clear that I'm dividing A by the GCD of an, since the GCD of the n dividing GCD of an and A divided by the GCD of an is equal to 1. So here we have that these two numbers are co-prime, because essentially what we're doing here is we're dividing both numbers by the greatest common factor between these numbers. So once we divide them by the greatest common factor, there is no common factors anymore between the two numbers, so they must be co-prime and their GCD must be equal to 1. So since this divides this, but this is co-prime to this, then this has to divide this number here. So we have that n over the GCD of AN divides L. So if this was confusing, just take an example like 5 dividing 10 times 3, right? 30. So 5 and 3 are co-prime. They share no common factors. So we are forced to assume then, we're forced to conclude that 5 divides 10. So 5 divides 10 because the GCD of 5 and 3 is equal to 1. And that is exactly what happened here. This number divides the product of these two numbers, the A over GCD and L, but since this number is co-prime with this number, that means we're forced to say that this number divides L. So we have this relation, and we will call it double star. So we have now star and double star, and we can combine these two results. So star and double star together gives us that L, which equals the order of G to the A, is equal to N over the GCD of AN, thus terminating the second part of the proposition. The third part of the proposition takes the same supposition here and the same supposition, except that more precisely we have that A is a positive integer that divides N. So to prove this, all what we need to do is take the result of the first proposition. So since A divides N, we have that the GCD of AN must equal to A. This idea is the same idea we've seen in the proof of the previous proposition. And we can say, simply using the second part of this proposition, in other words, this formula here, L is equal to N over this, which is equal to A, completing the proof of proposition 3. Okay, now that we have talked about proposition 3, which included all the groups possible, we will now narrow our focus again to talk about only cyclic groups, and let's see a special result that comes from that. So proposition 4 says that if G is a cyclic group, so G is a group made up of the powers of G, where n is any integer, then the first result says that if the order of small g is infinite, then we have that the group G is the group generated by G to the A if and only if A is equal to plus or minus 1. In other words, A equals plus or minus 1 are the only powers possible where G is generated by G to the A. The second result says that if the order of G is equal to L, which is finite, then we have that G equals the group generated by G to the A if and only if the GCD of AL is equal to 1. Let us get into the proof of this proposition. Let us now start proving this proposition here. The first part says that if the order of G is infinite, then we have this if and only if relation. So we're going to be proving both sides of this implication. The backward direction is pretty easy. If A is equal to 1 or A is equal to minus 1, then obviously G is equal to the group generated by G or the group generated by the inverse of G. That's pretty given because G is defined to be the cyclic group generated by G, which is trivial. So most of the work is going to be done on this direction. So if G is equal to the group generated by G to the A, since small g is an element in G when we take n is equal to 1, then this G is equal to some power of G to the A, because if G is equal to the group generated by G to the A, then G to the A to some power is equal to G. So G to the A to some power L is equal to G for some integer L. Okay? And G to the A to the L is equal to G to the AL. And now if we multiply both sides of the equation by G inverse, we would find that 1 is equal to G to the AL minus 1. So we have that G to some power is equal to the identity here. However, we know that also the order of G is infinite. So AL minus 1 cannot be a positive number, because if it was, then the order of G has to be dividing that number. So it has to be a positive number. So AL minus 1 is forced to be equal to 0, because the order of G is infinite, not finite. This means that A times L is equal to 1, and it means that A divides 1, because A times some integer is equal to 1. But the only numbers that divide 1 are either A is equal to 1 or A is equal to minus 1. Therefore, A is equal to plus minus 1, and the forward direction is completed. Therefore, both directions are completed, and the first part of the proof is completed. To prove the second part of the proposition, we want to prove this double implication right away. We're not going to do it both directions. So we're going to use proposition 1 to say that the order of a cyclic group is equal to the order of the generating element. So if we denote the order of small g by L, then we know, because G is equal to G to the n for n any integer, that the order of big G is equal to the order of small g, which is equal to L. So by proposition 1, we have that the order of big G is equal to L. We have that already. Now, if G is equal to the group generated by G to the A, then we will use proposition 1 again. So G is equal to G to the A. Using proposition 1 again, so using prop 1 again, we see that the order of G must be equal to the order of the generating element, which is G to the A. So the order of G is equal to the order of G to the A. But since the order of G is already said to be equal to L, that means that G to the A, the order of G to the A is equal to L. So the order of G to the A is equal to L. But because we've seen in proposition 3, part 2, that the order of G to the A is equal to L over the GCD of A and L, we can say that this is if and only if, so this is if and only if L is equal to L over the GCD of A and L. And now all we gotta do is divide both sides by L to get that 1 is equal to 1 over the GCD of A and L. And now we can just flip it around to say that the GCD of AL is equal to 1. Therefore, proving the double implication going from G is equal to the group generated by G to the A, all the way to GCD AL is equal to 1, completing the proof of the whole proposition, proposition 4. Okay, so what is the point of the theorem that we've just seen here? This theorem that talks about subgroups, the order of the subgroup, being every subgroup of G is either the identity or in this form. And then we see that for every A positive that divides N, we have a single subgroup such that this is true. So the whole point of this is to really outline the beautiful symmetry of cyclic subgroups in a cyclic group. So if we take this cyclic group of 12 elements, we call Z12Z with the addition operation. So go back to the clock exercise that we've done before. Very interesting stuff here will happen. So we will have a look at the cyclic subgroup. So for each image that I've put here, I will be denoting what the elements of the subgroup are. The first two subgroups are going to be the trivial subgroups made up of a single element, which is the identity, and made up of all the elements, which is the entire group. Remember, in lesson 9, we've seen that for any group, there is the trivial subgroups, which is the either identity or everything. So the first subgroup is just the identity given by 0 bar. The second one given by all of the elements in Z12Z. Okay, so let us use the theorem to see if it agrees with the result that we've seen. So we know that if G, the order of G is equal to N, so here G is Z12Z, and the order of Z12Z is equal to 12. Then for all A positive that divide N, so for all the A positive such that A divides 12, there is a single subgroup H of G such that the order of H is equal to A. So the positive A's that divide 12 are just the positive divisors of 12, which are 1, 2, 3, 4, 6, and lastly 12. For each and every one of these divisors, we get a single subgroup such that the order of the subgroup is that of A, and H is equal to the group generated by G to the N over A. So in the first example, we have that A is equal to 1, okay? And so we have that there is an H such that the order of H is equal to 1, and H is equal to G to the D, which is G to the N over A, and N is equal to 12, A is equal to 1, so it's G to the 12. Okay, but what does this mean in the context of Z12Z with the plus operation? Well, the G here, remember, is the generating element of Z12Z. And we know that the generating element is 1 because 1 plus 1 plus 1, any number of times gives us all of the elements of Z12Z. So this is 1. But is it the multiplicative power or the additive power? It is the additive power because the operation is addition. So instead of writing 1 to the power of 12, we write 12 times 1. And this is what we're going to be adopting for all of the subgroups of Z12Z. So it's going to be 1 times 12, and 1 times 12 is equal to just 12, but 12 in Z12Z is equal to 0. So it literally contains just the 0 element, because 0 plus 0 plus 0 is always equal to 0. And that's just the trivial subgroup over here. Now the other case is when A, So first of all, a is equal to 1, we have completed. Let's do now a is equal to 12. For a is equal to 12, we have that the order of the subgroup H is equal to 12, and H is equal to, now this time here, it's going to be 1 times 12 over 12, which is just 1, and this is equal to, you guessed it, 1, and the group generated by 1, well, it's 1, 1 plus 1, 1 plus 1 plus 1, and so it's going to be everything, all the elements in Z12Z. So this is going to be 0, 1, 2, all the way to 11, and then 0 again. So it's just going to be the entire group Z12Z, agreeing with the fact here that this is a subgroup of Z12Z. So now we have completed the case of a is equal to 12. What about the other cases, 2, 3, 4, 6? Well, for those, let's see. When a is equal to 2, so here a is equal to 2, a is equal to 3, a is equal to 4, and a is equal to 6. Okay, I must have put some extra clock here that I don't need. So I only need these 4 left. Okay, so a is equal to 2. We have that there exists a single subgroup H such that the order of H is 2, and H is equal to 1 times 12 over 2 by the same convention that we've seen earlier, and this is equal to 1 times 6, which is 6. So it is the subgroup generated by 6. So it's 6, 6 plus 6, and so on. But this only gives us 2 elements, which are 0 bar and 6 bar. Because 12 bar is just 0 bar again, so that's just 2 elements. So this is just when a is equal to 2. Okay, when a is equal to 3, we have the same deal, and H is equal to 1 times 12 over 3, which is 4, and so it's 0, 4, 8, and 12, which is 0. So it's 3 elements, as expected. When a is 4, we repeat the process. H is equals to 1 times 12 over 4, which equals to the subgroup generated by 3, and that's 0, 3, 6, 9. And so this gives us the case a equal 4, and when a is equal to 6, we have H, the order is equal to 6, and H is given by the subgroup generated by, okay, so it's 12 over 6 generated by 2. So the multiples of 2 are 0, 2, 4, 6, 8, and 10. And so this gives us all of the subgroups. There is no any other subgroup except those given by these A's, because of the first property saying that every subgroup H of G is either the identity, containing the identity, or equals G to the D, where G to the D is not equal to 1. And we've just seen that the D's possible are only the n over A's, where for all the a bigger than 0, such that a divided by n, we have these subgroups. So we've just detailed all of the subgroups possible of these cyclic groups just by using the properties and the propositions that we've seen throughout this lesson. So to represent these subgroups graphically on the clocks that I've put here, for a is equal to 2, we would have 2 elements, which are 0 bar and 6 bar and 6 bar and 6 bar. So for a is equal to 3, we would have 3 elements, 0, 4, and 8. For the next subgroup, we would have 0, 3, 6, and 9. For the next subgroup, we would have 6 elements, 0, 2, 4, 6, 8, and 10. You can see how visually nice and satisfying that is. So these make up all of the subgroups possible of Z12Z, and that can be generally applied for any Znz for all the positive divisors of n. And with this, we have finished Lesson 10, Cyclic Subgroups. If you've enjoyed this lesson, please leave a like and subscribe and share this with anyone who would be interested in this fascinating subject. I'll see you all the next time. Have a nice day and bye.